Now, our first speaker today is Dr. Bob Nichols, who's a faculty colleague here at JABSOM. He is certainly a highly productive researcher in the area of molecular neurosciences, and we're all hoping that his research yields information we can use to keep our memories fresh and our reasoning sound, the topics he will be addressing. And I rather like this quote about memory from Herb Caen. He said, "I have a memory like an elephant. I remember every elephant I've ever met." And I do too, so I must have a really good memory as well. So please welcome Bob.
Thank you, Virginia. So, aloha kako, good morning. Hopefully you did get good sleep last night. For those of you that think that you're going to be able to come here and learn about how to exercise while sleeping and perhaps practice that during the session, I'm afraid you're going to be disappointed. It's an interesting idea, though, so maybe somebody should work on that. Now, what I'm going to really focus on today is memory. That's going to be really what we're going to dive into. Talk about the memory systems in our brains. And in the end, these memory systems are really part and parcel of who we are. We can't have cognition without memory. Cognition is a very broad term that includes reasoning and remembering and imagining. And so our memory systems, not just in terms of our old memories, our reminiscing, but our ability to form new memories really are something that as we get older we want to preserve. We want to be as sharp as we can. And that is really a big part of who we are, what we need for day-to-day living, even doing simple tasks. Memory is at the root of everything. So I'm going to talk about memory and reasoning, more about memory. And there are two things really at the top of the list that we can do that can help with preserving your memory, making sure that it's functioning at the level that we all want. And that is sleep and exercise. There are other things that we can do to boost our memories. You can do certain simple tasks, simple problem solving. But in the end, these two things are what matter. And these are the easiest things that we can try to do. So I'm going to talk about sleep and exercise right off the bat. So obviously from an early age, we're told to get good sleep, right? And to be active and fit. And that's true all of our lives. And so it turns out that when older individuals over the age of 65 are polled in a survey, nearly half of them say that they have difficulty with sleep. And this can take on many forms. Difficulty going to sleep, difficulty in terms of how they feel after you sleep, and then what's shown here in this box, something that can develop, which is fragmented sleep. And this is where you wake up often during the night, and it's actually interrupting your normal sleep cycle. And I'm not talking about getting up to go to the bathroom, men. Okay, this is just breaking up your sleep. Okay, and we need that normal cycle. We need to go through stages of sleep to make sure that we can have proper reasoning and cognition later. So the other thing is that in that group, 1 in 3 say that they need something to go to sleep. Usually a sleep aid. A little closer? Okay. They need something. And I don't mean a glass of wine, right? I mean, okay, that can help, and that's used often. But I mean they'll take something, usually over the counter, maybe a prescription medication. And in that group as well, most individuals, nearly more than half, think that as you get older, you need less sleep. Okay, and I've heard that from myself from a young age. Individuals that say, well, as I've gotten older, I don't need so much sleep. I'm fine with it. Well, that ends up being a fallacy. It turns out, whatever your cycle is, we were talking earlier about how we know whether you've gotten enough sleep. That's for each of you as individuals. You may need 6 hours, you may need 8 hours. Whatever it takes to go through your whole cycle of sleep, that's what matters. But if you don't get that whole cycle, let's say you need 8 hours and you only get 6 hours of sleep, you'll accumulate something called sleep debt. And you may not need to sleep necessarily more the next day. You might do that for several days, and usually what happens is people catch up. They have a long nap on Sunday afternoon, and you think that's perfectly fine. You're actually catching up on your sleep, but you're not doing it in the proper way. You need every night to go through the right cycles, that is, the right stages of sleep. Okay. So what's the goal? Get good sleep and find the right exercise for you. Okay. And hopefully some of you were able to look back at a wonderful presentation by Dr. Saul from the Sleep Clinic, who went over all aspects of sleep, including issues that can arise when you do have difficulties in sleep. So we'll talk about strategies for sleeping here. We'll go over that at the end, but if it really becomes problematic, it really is wise to get help, because there's great help out there for getting good sleep. Okay. So what impact does sleep and exercise have generally on this cognition? Again, that's a very broad category, kind of a fancy term. It's about remembering, it's about reasoning, imagining, and problem solving, and also our use of language, understanding and applying language in our daily lives. So we know about the importance of sleep when it's not good. Okay, when you have poor sleep, there's difficulty in immediate recall or short-term memory. And I'm here to tell you that short-term memory is actually really fast. Okay, we usually misuse that term. We usually use it for recent memories, something that may have happened an hour ago or the day before. Now, you need your short-term memory processing to get those recent memories, right? But it turns out it's a real fast thing, okay? And second, of course, recalling those recent events is also impaired. You have slower, generally more slow reasoning. You know, if you're groggy, it just takes longer to think about things, and it's particularly manifested in trouble with problem solving, when you really have to figure something out. That's when you really see that, oh, I didn't have enough sleep and I really am not at my best. So why? Well, it turns out that during sleep, you consolidate your memories. So those recent memories have to be transferred into what we call long-term memories. Okay, so what does consolidated mean? Well, that means fixed and stable in the brain. Okay, so there are processes we're going to talk about where your memories kind of flux through your brain, but eventually they have to be spread out, and there are changes actually in how nerve cells interact at their contacts, which are known as synapses. And so memory, that's the basic unit of memory. So at your synapses, those synapses change, you may have more of them, they get stabilized, and that's where your memories are, okay? And sleep is essential for that. In fact, there's reason to believe, from a large body of research up till now, that a big part of why we need sleep is to consolidate those memories. And also to reset your short-term memory. Short-term memory has to be fluid and flexible. You need to be able to access it all the time. So it has to reset. And so those two things we actually need sleep for, and it's felt that we sleep to do that. Now, when we dream, it isn't that you're reenacting all your memories, right? But you're certainly cycling that information, okay? Poor sleep, then, impairs that consolidation, that fixing of those long-term memories. Now, long-term memories can take actually a very short time to be laid down, or they can take a considerable amount of time. But to be sure that they're fixed in the brain, you need that sleep. It also, poor sleep impairs attention. Okay, so attention, you need to focus, right? So if you're going to learn something, you better be focusing on that, okay? And then we talked about problem solving. Now, this may seem like it is coming out of left field, and it'll make more sense as we go forward and I explain it. But it turns out that during sleep, that sleep is required to clear a peptide from your brain called beta amyloid. Now, peptides are strings of amino acids, and they're derived from proteins, which are much longer strings of amino acids. And proteins are the actors in all your cells. They are the actors that carry out the functions in the cells. So peptides, though, are usually regulatory things. From our work in the laboratory and others out there, it's been shown that beta amyloid, which we all have, all our lives, it turns out, that it is in very low levels in the memory processing areas of your brain, okay? And it actually has a positive action. It is a positive regulator in the brain, and we've actually turned it a neuropeptide. It has a normal function. And like a lot of things that have a normal function, if you have too much of it, things go bad. So beta amyloid is, in fact, one of the pathological elements, one of the bad things that starts to accumulate before the onset of Alzheimer's disease. And that accumulation is enormous. It's more than 10,000-fold, and then everything goes haywire. So that's what then coalesces into these plaques that you can see in Alzheimer's, which we can now visualize with imaging, okay? So it turns out that this is just a hint that amyloid regulates at the level of synapses and it regulates particularly the synapses that have to do with fixing those memories. Okay. The other thing I'll mention is exercise, and this is all positive. So if you maintain your exercise, it turns out that that maintains the neurons in your brain. That's the fancy term for nerve cells. But more importantly, it actually can increase the number of synapses. And it does this in, again, the areas of your brain devoted to memory systems. Okay? And we'll talk a little bit more about that in a minute. So let's talk about how memories are laid down in a very general scheme here. Okay? In this flow diagram. So information comes in through our senses, and we recognize that through what we call our sensory memory. And we're very language oriented. So, for example, if you taste something that's salty, you associate that saltiness to that actual sensation, and all those sensations are recognizable. That's why you can recognize them out of this very separate type of memory or sensory memory. If it's a word, it's semantic memory. We'll see that in the next slide. Since we're very language oriented, again, all our other senses are coded often by a word or a phrase. Okay, so that information comes in, and building up from our experience from infancy, we recognize that thing, whatever it is, that sensation, that stimulation, in very general terms, almost instantly. Right? Now, we accumulate over the course of a lifetime tens of thousands of words in our semantic memory. You may not remember all the meanings of them, but you do recognize the word. So this is very, very fast with a word, okay? So then that is fluxed, in a manner of speaking, through the area of brain devoted to short-term memory. And the short-term memory is really like a register. Memories are not stored there, they're just held there and worked on. And in fact, the work that's really done in terms of thinking about that information goes yet to another part of the brain where that information, if it's just a word, is held in our working memory. As you can see, it's pretty fast, less than a minute. And then eventually that information gets transferred to our long-term memory, okay? And that might happen quickly. Some individuals have a photographic memory, or you're in a certain circumstance and you have that memory the rest of your life and you can retrieve it easily. Sometimes it takes a lot longer. Now, even though it's that memory is laid down for long term, you still need sleep to consolidate it, to fix it in your brain. Now, I'm going to do a little test, okay? I'm going to say a word, and this is not going to be a competition, all right? It's voluntary, and there are no points for being the loudest, okay? So I'm not going to count because that's actually going to interfere. We're going to talk about interference in memory in a little while. I'm just going to pause and I'm going to say the word, and if you can, say it back as quickly as you can. And don't worry how quick it is. Okay, is everybody ready? I'm going to count to myself to 3. Okay, ready? Monkey. That was pretty fast. Okay, so what happened? You instantly recognized that word, right? And you retrieved it from your semantic memory, from your sensory memory. You put it into you flexed it, I should say, through your short-term memory. You put it into your working memory, which is, again, a different part of the brain. And you held it there, and you didn't need to hold it there very long. And then you accessed it, and then you created what's called a motor output. That is, you drove your vocal cords in your mouth to say the word. And the other thing I'd like to say for the record, Virginia, is that the class called me a monkey. And that was a declaration, by the way. So let's talk about the different types of memory. And we've already alluded to the first category here, declarative. And it's easy to remember because it has to do with declaring things. Okay, so we have the semantic memory, so that's what we call basic knowledge, but it's basic units. It could be words, numbers, symbols, images, and we can access those, again, very quickly. So when you heard the word that I said, this was almost instantaneous, you heard it. Okay. Now, if we string together a number of things, they could be sounds, they could be sight, whatever senses are component to some event, that we call episodic memory. Okay. And that is usually broken up into small pieces. So if you go to a movie, you can think about the scenes in the movie, so that's how we really encode memories, even parts of scenes, and then we string them together. That's all very discrete, that uses particular parts of the brain, okay, particularly episodic memory. Episodic memory really depends very heavily on a particular part of the brain, the so-called hippocampus, which I'm going to show you in a minute, that is essential for short-term memory processing. Now, on the other side, there's what's called non-declarative memory, which was named because someone had no imagination, and they said, well, it's not declarative, so we'll call it non-declarative, right? And there are all kinds of different types of memory under that category, but the most important one is procedural, and this is for skills and abilities. So, for example, riding a bike. Now, I haven't gotten on a bike for a while. I imagine some of you ride bikes all the time, or maybe some of you haven't, but I guarantee most all of you could go outside and get on a bike and at least automatically know how to ride that bike, and you can get on any type of bike. So it's highly flexible, it's automatic, and it's what we often call motor memory. That's encoded in a completely different part of the brain, and it's not affected by any kind of change in short-term memory. It's not dependent on short-term memory. Okay. Initially, short-term memory does contribute, but in the end, once you access that memory, it doesn't matter. You can just do it. Okay. So I've already alluded to this. Where do these memories happen in the brain? So this is a picture of the hippocampus. So what is shown here, up in the upper right, is a cartoon of the brain. So you can see the front of it, the back of it, and along the side here, you have these lateral lobes that are known as the temporal lobes. And underneath there, buried, this blue bit is the hippocampus. You have two, so they are hippocampi. Hippocampus comes from the term seahorse. And so if you take a section here through this part of the brain, okay, and you look at it face on, we call this a coronal section, and you can remember that because of the crown. We can work our way down. So here's the inside of the brain, the outside, and if we work our way down, we can see this big groove here that is a demarcation line for the temporal lobe. And if we keep working our way into the inside, we can see this little loop of what's called the cortex. Okay, that's really sort of this, the outer layers, the skin, if you will, of the brain. Okay, it loops back on itself, and so it looks a little bit like a seahorse. And there's a beautiful diagram down here by the great Italian anatomist Camillo Golgi that he drew well over 100 years ago that shows the enormous complexity of this part of the brain. And this is a section. So the circuitry, we now know, is well defined and functions in large part as a register. And so along the hippocampus, it's replicated all the way, even though it bends around. All along the way, there's a whole series of registers. It's actually, even though looking like a small structure, has an enormous capacity. Okay. That is where short-term memory happens. And it's a processing station. Memories are not stored there. They flux through there. They are processed there, and they're sent somewhere else. Okay, where's that other spot? Well, the other spot is the prefrontal cortex. This is in the front of the brain, and it's easy to remember because front's in the name, right? It's prefrontal cortex. So in that region, there's another register, quite large, that then holds whatever you have processed through your hippocampus that you want to remember or work on, right? So you held that word in your prefrontal cortex. Before then, you integrated that with association areas, particularly a more fancy naming area called the parietal cortex. That's association cortex that helps to integrate sensation and help to generate patterns that ultimately go to your what's called your motor cortex for you to say the word, okay? But the prefrontal cortex, that's the memory register for working memory. And this is actually an overlay of activity measured with an MRI for an individual doing some kind of a working task. And you see those areas of the brain light up. And interesting, they light up early, okay? Long before then, the areas of the brain that light up, that by light up I mean are now very active to generate that motor output. That is, say the word, for example. Okay, so I already alluded to this. Ultimately, it's at the level of synapses in the brain, and it's spread over different areas. And we actually understand now at the molecular and cellular level, but we're not going to do that deep of a dive here. Fundamentally, synapses change to encode your long-term memories. And fortunately, we have a lot of them. So we have upwards of 100 billion neurons, fancy name for nerve cells, in our brain, and each neuron on the average has about 1,000 synapses. So if you do the quick mental arithmetic using your working memory, okay, you have 100 trillion synapses. Okay, there's not that many galaxies in our universe. I mean, it's an extraordinary number. We basically have more than a universe in our brains in terms of capacity. Okay, and so what happens then is the information's encoded in those synapses. I told you they're fixed and stable, but before they're fixed and stable, it turns out that the synapses are really dynamic. They can be ramped up and become more effective, or they can be ramped down. This happens primarily in that hippocampus, in that short-term memory register, because you got to reset it. It's got to be able to turn back over. Where it's fixed and stable, then, in the other parts of the brain where you have your memories encoded, they're not so dynamic. So not only do you have 100 trillion of these synapses, but many of them they're not just on-off switches, they have this full range of dynamic nature. I find that extraordinary. I'm still fascinated about the synapse, even though I've only been working on it for 40 years. Okay. So how does the hippocampus work? So I already told you about the short-term memory part and how synapses are quite plastic in that system, or flexible. Okay, but the other thing the hippocampus does, this is a little bit of an aside, but it does relate in terms of cognition and actually laying down memories. It actually maps our environment. Okay, so all those registers actually, moment to moment, are registering your environment. And even if you turn your head, you're just constantly mapping that. There's actually what are known as place cells in the hippocampus that you can get activated by certain things in the environment. And it turns out our memories are very much encoded by our sense of place. And if you think about, well, this is Hollywood, right? But if there's a detective show and they take you back to the scene of the crime and somebody's a witness there, it's like they'll have a better memory of what happened by taking you back to the scene of the crime. So it's kind of like that. Your memories often are linked. And they're also linked to your emotions. And so these little yellow dots in the front of the hippocampi here have a funny name as well, amygdala. I don't actually remember where that name came from. But at any rate, that is where you have the primary central circuitry for your emotions. And that area of the brain is not just because it's in the right place, it's heavily connected to the hippocampus. And so basically all of your memories are colored by emotions. And your emotional state can matter, okay? If you're very low, it can be very difficult to someone who's depressed, has great difficulty in processing memories, and it's very high. So you want to be in between, but if it's slightly elevated, your attentional, some of that's attentional, your focus is higher, and your memory processing is a little bit better. Okay. So the other thing that we know about how the hippocampus works comes from patient stories. Okay. So there are two prominent case examples. The first one, patient H.M., passed away, so we know his name. But in the 50s, lived in Connecticut and developed what's called intractable epilepsy. Okay, so this was localized to those lateral or temporal lobes. So the treatment then was to pull them out. So they were excised, and that excision also involved most of the hippocampus on both sides. So patient HM, Henry Mollison, couldn't form episodic memories, but had perfectly good long-term memory, and was actually the first clear example where we understood that short-term memory, okay, the short-term memory processing was completely separate and contained in the hippocampus from the long-term memories, which are put somewhere else. Okay. There's also someone who's still alive now, Clive Waring, who was a musician and a conductor, but he's a pianist. He had a rare viral infection, and so most of his hippocampus was damaged on both sides. And that can be imaged, you can see the scarring. Okay, so he had a little bit of short-term memory, but it was very, very short, up to 30 seconds. Okay, so if he met somebody, turned away, came back, he wouldn't remember who they were. But he could play pieces on the piano. He would sit at the piano and he'd just start playing, and he'd play it all the way through perfectly. So that procedural memory was completely intact. And of course, all of his long-term memory was intact. So he'd play that piece on the piano, wait a minute and look up, and someone would say that was a wonderful piece by Bach, and he would say, what are you talking about? So that also basically confirmed as well that the hippocampus is essential. But his was damaged, it wasn't gone. So it turned out he could learn new pieces on the piano if he had short little stretches that took him no more than 30 seconds to play. So he could piece them together, and then he would start to play these pieces, these new pieces. So even though that hippocampus was damaged, there was enough of it there that could still process a short-term memory. And then someone would say, well, that's a wonderful new piece that you learned, and he goes, I never learned that piece. So it was remarkable, though, with regard to him being able to cope with life, because this was really a devastating thing to happen to somebody. Okay. So what happens with age? All right. Well, with age, some things are pretty well preserved. All right. So our declarative memory actually really isn't that bad. Your semantic memory is also very well preserved. That decays, or decreases, I should say. I said to myself I shouldn't use the word decay, even though I feel like I'm decaying every day at my age. Okay, semantic memory is quite well preserved. Episodic memory is actually still pretty good, but your capacity decreases. Okay, what do I mean by that? Well, at a certain age, could give you a list of words, say 10 or 12, and you can remember all of them. And as you age, that list gets shorter. So there's a clear example. Hopefully it doesn't get down to, say, much less than 4 or 5, but that happens. And that's just because you're reducing capacity, and some of that has to do with normal changes with aging in our brain, at the level of the neurons and the level of the synapses. It just happens. And then there's difficulty with retrieval. The conversion, though, to long-term memory is also less efficient with age. So if you have a reduced capacity and your conversion to long-term memory is hampered as it happens with age, you do have a general effect in terms of being able to lay down memories. This is just the fact. Working memory is actually the worst. Okay, so that decreases with age significantly, but it turns out it starts to decrease after the age of 30. So if you have children who are 30 or older, you can tell them, you're not like you used to be anymore, right? So what are the examples of working memory? I told you about holding that word in your memory, but more clear examples are like mental arithmetic or reordering a word list, okay, that was not alphabetical, but you render alphabetical. Okay. And so, not only is the working memory decreased, well, that's a fact of life, but it turns out as we get older, then something called interference has an impact. And that could be just background noise, okay? It could take a lot of different forms. And so part of that is attentional, focusing, but some of it is actually having too much stimulation coming in and having your brain sorted out, okay? Now, procedural memory, that is completely intact, okay? Basically your whole life. And even if you start to show significant changes in your episodic memory or your ability to lay down memories, that procedural memory stays. Now, I'm going to show you a test for working memory to demonstrate the interference, and in this case, you can just do it yourself. We're not going to do it as a group, okay? And this is an interesting case of a very simple test, but a very powerful test, where you're to look at these words, and they're not in your book, okay? So I didn't want you to see them ahead of time, all right? No, cheating, all right? And you're supposed to look at the word and say the color. Ooh. A little more tricky, huh? So the first word is red, and you're seeing red, aren't you? Okay. But it's blue. So it takes a second to say, wait a minute, that's blue, that's green, that's red, that's yellow. I have to look at it. So now if I had just given you those words or told you just to say the words, you could say them very quickly. Now what were the colors? Ooh, this is tough, isn't it? So remembering that as well is tricky. So since we're so language oriented, word oriented, you read the word. If it's hard to get past the red, that's blue, all right? And now we can mix this up and do this over and over, and you'll actually get better at it. So you can use this test for a number of different things, for attention, for recall as well, all right? So it really is a very powerful test indeed. Well, it turns out that as we get older, you can do the Stroop test, and you can find it takes us a little longer to do it. But it turns out with Alzheimer's disease, it takes individuals more than twice as long to do the Stroop test. It's not used diagnostically. This is usually with somebody who's already been diagnosed with dementia, with Alzheimer's disease specifically, but really across dementia, that's true. Okay? And it's a classic example of how working memory, even though we think about short-term memory with Alzheimer's disease, the working memory is severely impaired. Okay, so I went through all this, and as we get older, things start to I won't use the word decay, but they start to decrease, all right? So fine, what are we going to do about it? Well, it turns out social scientists tell us that as older individuals, we have much better coping strategies. And so this is what we need to rely on. So we are better at using mnemonics, not quite like what's shown in that lower right by that cartoon by Harris. I mean, that's not a really good idea to memorize really long numbers, associating them with some inanimate object. But we do use mnemonics, and we're practiced at that, but we are better organized. We're very good at recording information, manipulating information, and this is a biggie. Based on your experience, you can translate between tasks because there's familiarity. And because we're so flexible and what we call plastic and adaptable, something will seem familiar, so now you go to a new task and you can apply that experience to it. We're very, very good at it. And we're also really good at evaluating and utilizing resources, and I think that's why we're much better probably at using the internet than younger people are. But at any rate, those coping strategies, okay, are to be relied on. So as you get older, for healthy aging, keep those in mind. And if you feel kind of funny about using these strategies, don't. Use whatever strategies help to aid you in your memory, which is always going to help you with your cognition. Now, I'm not going to go through this in great detail, but with Alzheimer's disease, you do see declines in all aspects of memory. And of course, when we talk about one of the earliest events, various changes, in Alzheimer's disease, this is with episodic memory, which heavily relies on your short-term memory processing, which I told you is quick, right? But this is all on the level of changes that are happening in the hippocampus. And it turns out early changes happen to the synapses in the hippocampus before they disappear. So eventually they do disappear. Alzheimer's disease is neurodegenerative, so synapses are lost and then neurons are lost. There is a much later decline in semantic memory, and it's somewhat insidious, and it is progressive. So initially there's difficulties with word retrieval here and there. Now, there are occasions when I have trouble with people's names, and so, that's not necessarily a sign of this. This would be more common language usage. Again, hippocampus. Decline in working memory, we already talked about that. And then remember I told you that the hippocampus orients you in space? Okay, so later on, the damage to the hippocampus leads to difficulty in orienting and, in fact, getting lost. And there's issues in terms of selective attention because you also have changes in the frontal cortex. Again, that's what's happening to show where it's manifested as a change in working memory, but you also need the front of your brain heavily for attentional aspects. Okay, we've talked about Alzheimer's disease in terms of this beta amyloid. Okay, but the first clear loss that you see in Alzheimer's disease is at the level of the synapses. And this happens predominantly in those areas of the brain that have to do with memory. That's why we think of Alzheimer's disease as a memory disease, and that is true. Okay. Actually, again, before those synapses die, they start to lose their function. They become uncoordinated. Well, it turns out that this beta amyloid, which we normally visualize as plaques in the brain, the lower right there is showing a stain for these plaques. They do accumulate in Alzheimer's disease, but I'm going to tell you, we all have them. There's individuals that have a heavy number of plaques in their brains all their life, live into their 90s, be sharp as a tack. What we do know is actually the beta amyloid that's floating around, the total load of the amyloid, is what's mattered. And this is something that we started research down this area that started to make sense. How could these balls of these, basically like little tar balls in your brain, these plaques, how could they do anything? Well, the amyloid, it turns out, interacts with your synapses and affects the function of the synapse that I mentioned before. Okay. And it turns out that happens. This is a visualization showing the regions of the brain where you get the deposition of that's the plaque formation of amyloid. And what that really is showing is where the concentration, the load of amyloid is the highest. Once it really is high there, then it basically kind of precipitates like a chemistry experiment, a bad chemistry experiment. So you see it accumulated in that temporal lobe, and it accumulates very heavily in the hippocampus and in the frontal lobe. Those two areas that we know have to do with key aspects of our memory processing. Okay. So how does this all relate to sleep, where we started from the beginning? Okay, so we're going to connect the dots here. But we have to talk about sleep and the phases of sleep and then make the connection. So whatever, again, your normal cycling of sleep is, all right, whether that's 6 or 8 hours, you need to go through these two phases, this early phase and this late phase, and you need to go through these different stages. In the early stage, you go through long periods of what is called slow wave sleep. We measure that with I don't do this. Okay. It is measured with electroencephalograms or EEGs. Okay, so you measure general brain activity, and it quiets way down. So the activity goes way, way down. Well, we actually know, as a little hint here, that beta amyloid is linked to activity in the brain. Okay, so at that stage, though, this is when the duration of that slow wave sleep has the biggest impact on episodic memory. Okay, you need that, and you need to have enough of it. So it actually is very early in your sleep cycle. That's completely dependent on the hippocampus, all right? And again, we learn things by when they go bad. So if you shorten your slow wave sleep, okay, it turns out that has its major impact on the episodic memory and the use of that episodic memory to lay down long-term memories. That is consolidation. The late phase, that's when you have the REM sleep, the rapid eye movement sleep, and that's when you dream, okay? And for a long time it was thought that's the period of the phase of sleep that you need for your memories. Well, it turns out that's true, but that's primarily for your procedural memory. In the end, you really need the full complement, the full cycling through these stages to fully consolidate your memories. But the episodic memory, which is key for you then turning that into long-term memories about things and people and events, that's early on. So if we reduce that, we see that you reduce this consolidation. Why? Because if you reduce the amount of quiet brain activity, that means it's more active. If it's more active, then that's where amyloid comes in. Okay. As I mentioned early on, a big part of sleep is to clear amyloid from your brain, and this is showing it in actual fact. So during the phases of sleep, and this was done on this graph in the upper right, is a measurement of beta amyloid in the cerebral spinal fluid. Okay, and that's a window on the brain. So it's a spinal tap. Sounds nasty. Spinal taps actually aren't all that nasty. They're a great window on the brain. So this is after midnight here, starting to go into slow wave sleep, and with a delay of a few hours, you see a big drop in amyloid levels, and that happens every single night. It turns out that beta amyloid is produced and cleared from your brain at an extraordinary rate. There are no other peptides in the brain, or certainly proteins, that turn over this way. The whole complement of beta amyloid in your brain turns over twice in a day. The only other kinds of things that do that are metabolites or metabolic things like glucose. It's extraordinary. This amyloid is just fluxing through our brains every day, so you need to get it out of there. And it's fairly clear now that defects in clearance lead to accumulation of amyloid. The other thing, though, is if you're sleep deprived just for one night and you look at the amyloid levels, they spike up 2 to 3 times in the CSF. So now you're going to have an amyloid debt. You have a sleep debt, you have an amyloid debt, and so later then you have to start removing it from the brain because it's produced at such a high rate, you got to get rid of it. So normally, we get rid of it just fast enough to keep up with that production. So it becomes a problematic cycle that you'll start to see when the beta amyloid levels are increased. So it works both ways. Sleep is necessary for removing the amyloid, and we now know that amyloid has an impact on controlling sleep. So the amyloid levels fluctuate with our daily rhythms, and that actually has it is one of the drivers for sleep. It's not the driver, but one driver for sleep. So if amyloid levels start to rise up, say in dementia, okay, there's other situations where that actually happens, then you start to have an impact on, and that's happening for one reason or another, probably from metabolic processes, that is your ability to just remove the beta amyloid from your brain, but then it starts to affect your sleep. Okay, so it starts to affect that slow wave sleep. Okay, so it's starting to shorten slow wave sleep. So what's happening? You're increasing the amount of neuronal activity at night when you're sleeping, and more neuronal activity means more amyloid. Amyloid is absolutely, its production is linked to how active synapses are. Amyloid's made at the synapse, and more activity, more amyloid, less activity, less amyloid. Now, normally, we use that as a way to regulate our synaptic communication. So it goes up a little bit, it goes down a little bit as synapses change. This is what we've been studying for years. But now this is going haywire. It's going up too much, and now it becomes a feed-forward problem because it's affecting the slow wave sleep, which is making more amyloid, which is affecting sleep, and so on. Okay. And in the end, of course, it's affecting this consolidation. Okay, so haven't really touched as much on exercise, and again, it's still all good news. So with exercise, and it doesn't have to be all that strenuous, in those memory processing areas of your brain, the hippocampus in particular, there's also some evidence in the prefrontal cortex, okay, that exercise maintains your neuronal numbers. Now, normally you get your complement of nerve cells, you know, by the age of 2. You have most all of them when you're born, okay? And they're what's called postmitotic. They don't divide. They're there. They stay there. But there are some new neurons that are made and lost, particularly in the hippocampus, and that is linked to memory processing. That's a whole other arena, but nonetheless, they do contribute. But more importantly, the synapse number changes, okay? So that happens every day. Now, that does decrease with age, all right? It's interesting, though, in terms of what we've learned in the last 10 years, is that the signals for that are coming from muscle. So they're just listed here as signaling molecules, but we now know that these molecules are released from the muscle with exercise. They go to the brain, and they produce a very fancy-sounding hormone called brain-derived neurotrophic factor. We call it BDNF, okay? And it turns out BDNF is a key player in stabilizing, in increasing the number of synapses and stabilizing them for consolidation. So our muscles have a lot to do also with consolidation in the brain, okay? And it turns out the exercise doesn't need to be all that intensive. Short, moderately intensive exercise works. Now, that's for memory. You want to have as much exercise as you need for cardiovascular health, okay? Now, I'm not going to go through this. There are a lot of approaches that are being studied for treatment of Alzheimer's disease. Some of this we're doing ourselves. A lot of new ideas, a lot of old ideas that didn't work, okay? But actually, none of this is ready for prime time. But sleep and exercise have been clearly shown to have an impact on symptoms of Alzheimer's disease. That does not affect the course of the disease. If someone is going to progress with Alzheimer's, I'm afraid it's going to happen. It may well be delayed to some degree, but people will function at a higher level. And of course, as we said from the outset, this is important for healthy aging, okay? So get good sleep and moderate exercise. So if you have family over and they're staying late, you can say to them, you have to leave. I need to get good sleep because I have to clear my brain of amyloid. So go home. There's a couple other things, though, one of which our own Kamal Masaki, who's the chair of geriatric medicine, you're going to hear from her in a few weeks. She did a very large study looking at our Hawaii, Asia cohort, that is a population of information that we have from a very, very large study here in Hawaii, one of our true gems in clinical medicine, to show that control of blood pressure, where in the context of hypertension, reduces risk. The flip side of that is, was shown for many years that the number one thing that correlates best with Alzheimer's disease is hypertension. Obviously, that's not the whole story, but just in terms of clinical symptomology. And if you control blood pressure, that has a significant impact. Okay. So to wrap up here, I'm going to talk about very briefly the guidelines for good sleep and exercise. And again, strongly encourage you to go back and look at Dr. Saul's presentation. He also talks about issues that can come up, and there are a number of clinics around the state where if you have difficulty that you can't address yourself in terms of sleep, that can help you out in a big way. But certainly we have to be cognizant and obey our daily rhythms, okay? So you should go to bed at the same time and get up at the same time, and that helps you to set your daily clock system, okay? And then if you nap, it's okay. Keep it short. It turns out in sleep studies that more naturally we should nap. Okay, so if you do nap, you can say, well, this is natural, but you have to keep it short, and you have to make sure that it doesn't interfere with your normal sleep cycle at night, so you can go through all those stages of sleep. And if you do dream, then you know you've gotten through that slow wave sleep cycle. No caffeine afternoon. Caffeine has a fairly long half-life in the body. It's about 5-6 hours, and we tell our medical students through medical pharmacology that there's the rule of 4. It takes 4 half-lives for something in your body to get out. So caffeine that you drink in the morning is just leaving your body by that next morning, okay? And of course that ramps you up, helps to keep you awake. And then chocolate has caffeine-like compounds, and if you have it late, that can have an impact on keeping you up. Alcohol, moderate amounts can be stimulatory. Don't eat late in the evening. Don't exercise late in the evening. Anything that amps you up is going to make it harder to fall asleep. You probably might have an okay sleep cycle, but you're just having a hard time falling asleep later. Relax, be comfortable. And one thing that I'll add that I didn't list here, but I came across not too long ago, is that if you're sitting up at night and you're thinking about something and you're pondering about it, you should turn on a weak light, get a piece of paper, and write out what you're thinking about, and maybe even a solution. And it may end up the next day seeming kind of crazy, but do that, and then put it out of your mind, turn the light back off, and go back to sleep. And for a lot of people, that helps to stop thinking about that thing that you need to do the next day that you were supposed to do 10 days ago, by the way. Okay. And then exercise, again, all good. So moderate, in terms of memory processing, moderate exercise. And it can be fairly short, 15 minutes, but certainly a half hour is good. Doesn't necessarily have to be every day. But this, in terms of memory processing, is enough to boost that neurogenesis and that synaptogenesis to help, or at least maintain it. Of course, you should get more exercise for cardiovascular help. But, and all kinds of strategies that help you with exercising. And I know that's a challenge, but, again, if you do it with friends, you do it with music, whatever helps, and you can do it sitting, whatever you can do, whatever you are capable of doing to get it intense enough, that will help. So I'm here to take questions, and I'm also interested in any comments, anything that you would like to suggest with regard to strategies or even issues you've had with regard to sleep and exercise, or any other questions about memory processing in the brain. I'm also willing to talk a bit about Alzheimer's disease, but perhaps we can save some of that for the break. Okay. Thank you.
I was really relieved to hear that the decline doesn't start until you're 30, because I'm 29, again and again and again.
Yeah, and again and again.
I have a question about directionally challenged people. Is that a problem?
What is that?
If you're directionally challenged,
Directionally challenged. That's, well, you do need your hippocampus for that. That's usually manifested at a very early age, and people don't usually get any better at it, and they don't necessarily
noticed
get any
that.
worse at it. And I know many examples of that in my own family. I think the phone helps a little bit, as long as you have it the right way up. Okay? Thanks. Yes?
I have a question. You were talking about the memory, in particular word memory. I'm bilingual. My grandchildren are trilingual. What does that do to memory building, long-term and short-term memory?
It's interesting, individuals who are bilingual or more, there are actually trilingual individuals out there, you actually are much more facile at laying down your memories. Because you have two different languages, and so I'm not perfectly bilingual, but I do speak French, and so I know that the whole construction and expression in that language is different. So you use that, particularly in terms of what we call executive function. So individuals that are bilingual tend to have, they're a little bit more facile. It's a little easier in terms of certain types of working memory processing that you can use for certain types of tasks. So I'm not saying everybody should go out and learn a language, but why not, right? But in terms of that, it's really quite interesting, a whole story unto itself. And of course, a big part of it is how we access our language areas too. And so that definitely has an impact to a degree in terms of overall reasoning to some degree. It's subtle, but it's there. Because again, you have very different type of thinking in one language as compared to how you express yourself. And so it does have an impact. Other questions?
Thanks for your lecture.
Yes.
And now if I can remember my question.
I was waiting for that one. Very
Seriously
good.
though, sleep versus exercise.
Mm-hmm.
Should I set my alarm clock to get up and exercise, or should I sleep in?
Should you sleep when you should be exercising? Well, I told you, maybe you could figure out a way to exercise while sleeping, right? Sleep really has the biggest impact. I mean, that probably is the biggest issue in terms of our memory health, if you will, as we age, and certainly in terms of Alzheimer's disease. Okay, so, but you get the bonus, of course, the necessity of exercise for cardiovascular health. Yeah. In the back.
Are there any pharmaceutical interventions that might help with reducing the beta amyloids?
We're working on that. So actually, in terms of reducing it, that has been a systematic failure. Okay, so almost every pharmaceutical company has addressed that by using, say, an immunological approach, like a vaccine, or what we call passive immunity, giving antibodies to people to lower amyloid. And you can show in the cerebrospinal fluid the amyloid comes down. But the individuals in clinical studies have to be diagnosed. The FDA does not approve studies for risk, although they're changing their mind about Alzheimer's. So these individuals have Alzheimer's, they're pretty far along. The amyloid comes down and there's been no effect. So we're studying a very different approach to interfere with the toxicity of beta amyloid in the brain rather than just lowering it. And we're a way, in fact, well, in a manner of speaking, treat through neuroprotection. So right now, there's nothing out there. And we're talking about hundreds of billions of dollars of failure. It's really been quite devastating. But there are some very new ideas on the horizon. Other question there?
Does one lose the ability to multitask as you age?
Yeah, so that you need your working memory for that. So that's what's happening. I just gave the example of one word, but normally with working memory, you're putting a lot of things in those registers and trying to integrate them and act on them, I will say, work on them. I guess I have to talk about work for working memory. Yes, absolutely. That will decrease to some degree. But the easiest thing is to try to break things up, right? Don't multitask. Yes. Okay. Yes.
There's a lot of advertisement for brain exercises. Do those help?
Yes. Well, they're perfectly fine to do. They can help a little bit with mnemonics to help, and reinforcement. Recycling your memories. Retrieving them and reliving them can help. So if you've forgotten something, if you think about it again, that helps. But these exercises, I mean, they're certainly fine. They can improve memory a little bit. I'm going to tell you they have no impact on the progression of Alzheimer's disease or the risk of getting it. And that's unfortunate because they're advertised, I think, sometimes not so subtly in that regard. There's really nothing you can do necessarily yourself if Alzheimer's is going to come, I'm afraid. Other question? Yes.
I wondered, sometimes when I get up in the middle of the night, go to the bathroom, I would have been waking up from a dream. And when I go back, I can continue with that dream, it seems.
Well, that's a very interesting thing.
And so
That's a whole nother subject.
Yeah,
What was the dream about? Do you want to share your dream? Okay.
So I wondered about the sleep cycle. Is that sleep cycle continuing? Or
It is continuing, yes. So the fragmented sleep I was talking about, where somebody's coming out repeatedly, and we're not talking like once or twice. It could be happening every 15 minutes to a half hour. So it really is disruptive. And again, it's happening in both slow wave sleep and REM sleep. So you can pick up where you left off if it's just once.
But in general, if you get up to go to the bathroom or whatever in the middle of the night and you go back to sleep, is your cycle continuing? Or
Your cycle should continue.
It doesn't go back to
it's
the
better to
beginning.
stay asleep the whole time, but by and large, it will continue. It may not be as perfect. You might have some interruption in some of these stages. So you notice that the stages actually cycle. You even have REM sleep early on. Didn't point it out, but in that early phase, it spiked back up. So you might not go through all of those cycles. And that was just an example. Everybody's cycling is different. So by and large, if you're able to do that, if you can sleepwalk, it's better, right? And urinate walk, I guess. So but if you can go right back to sleep, then you're probably going to be okay, because you have to, you'll start, you'll start your cycles again. Other questions? Yes. Yeah. Yes.
How do meditative states compare with sleep as far as eliminating
Interesting
amyloid?
question. Meditation does have an impact as well. It's a little bit more subtle because you're quieting your brain down as well. So that has only been preliminarily studied in terms of amyloid, but it's a really good question. But it does seem to have an impact. Going into meditative state for a sustained period, at least 15 minutes to a half hour a day does have an impact. It's more subtle. Sleep's at the top of the list. Got to get good sleep, and if you don't, it's very disruptive. But that's an interesting question, and it's something to think about.
Let's give Bob another big hand.